In this video, we'll be discussing about the installation of Ubuntu Linux, Autodock Vina, openbabel for the preparatory stage of molecular docking process. Click on the Start button and search for Microsoft Store. Here you can get all the applications which is compatible with Windows. Now search for Ubuntu and install the latest version. Here you can see I have already installed Ubuntu version 20. For the tutorial purpose, I will be showing the installation of Ubuntu 22. Click on to Ubuntu 22 and click Get. Once it is installed, to access the application you may need to turn on the Windows feature. So search Turn Windows feature in the Start button. Go down and mark the Windows subsystem for Linux. Here I have already enabled it. If you are doing it for the first time, once you enabled, you may have to restart the system. Click OK and wait until it loads. Now the Unix username creation will happen. You can give your name or anything else as a username. Here I will be typing my name and then we'll have to set the password. As a security process, these Ubuntu will not show the password, but you can type the password. Now this is ready. Now type sudo space apt-get update to install the latest version of the packages that are currently installed on this system. This step will take a little time. This will have all new packages available which will be retrieved and installed. Once it is updated, you need to do one more step. Type sudo space apt-get space upgrade. This step will download, install and update each outdated packages and dependencies on the system. But just running sudo apt-get upgrade will not automatically upgrade the updated packages. You will still have a chance to review some changes and confirm that you want to perform the upgrades. Now you need to type Y, which is yes. Next step is to install Autodock Vina. Type sudo space apt-get space install Autodock Vina. Oh, I missed putting install word in it. If you need to type the same command again, you don't need to type everything, just press the up arrow. Now add install after sudo space apt-get. Then enter Y. Next, very important tool is openbabel, which we'll be using for preparation of compounds in different formats. Install it by typing sudo space apt-get space install space openbabel. Type Y and enter. Openbabel will be used for further splitting of bulk compounds to individual conversion of SDF to PDB-QT and many more chemical conversions. Basically, it is a collaborative project allowing anyone to search, convert, analyze or store data from molecular modeling, chemistry, solid-state materials, biochemistry or related areas. It can convert over 110 chemical file formats. Now the Linux subsystem is ready for the docking process. Protein and ligand preparation. In this video, we'll be focusing on preparing the protein for docking process. Let's begin with the retrieval of protein from rcsb.org. RCSB is nothing but a powerful tool for exploring 3D structures of biological macromolecule for basic and applied research purpose. It is one-stop shop for 3D structural data. Let us take an example of MMP9 protein with which we can dock several compounds. Here I am going to download MMP9 inhibitor complex. You can find its details and publication. Now click download file and then click on the PDB format to get the protein in PDB. Now we'll have to remove the water molecules and ligands from the complex to make the monomer of protein for docking process. Open the protein in Discovery Studio Visualizer. Now you can see the red dots which are water molecules. Then two chains of protein along with the ligand. Now when we click on the ligand group, we can see it as highlighted in yellow. This and this. We can remove that ligand by simply pressing the delete button after selecting it. Then delete HET-ATM. Now we have two chains of protein. Let's see, is there any difference among each chain? Chain B starts with aspartic acid 113 and ends with tyrosine 443. Whereas chain A starts with phenylalanine 110 to tyrosine 443. If both chains are the same, one over other can be considered for molecular docking process. So I'll be deleting the chain B for further steps. Now we have the protein monomer without any ligand or water molecule or additional chains. Let's save it as 1GKC filtered. Now close the Discovery Studio and open Autodock tool. All details are mentioned in the description if you need to install these softwares. It will take a little time to load. Once it is opened, you can drag the prepared PDB inside this tool. You can see there is only one chain now. Click on Edit and add hydrogen. Then mark polar only, then click OK. Now you can see the hydrogen atoms are added on the proteins. Now go to Edit again, go to Miscellaneous and check for missing atoms. If there is any, you have to select those and click on the Repair Missing Atoms in the same section. Close and click on the Edit again and then go to Charges, then add the Coleman charges. Since in PDB files, hydrogen atoms and charge is missing, so generally these charges and hydrogen atoms are added for proper optimization. Now check the charge on the total residue. It's showing no residues with non-integral charges found, so it is good to go now. Next thing is we have to save it in the Autodock format, which is PDB-QT. Click on the grid and then click on Choose under Macromolecule. Click on the 1GKC filtered and then click the Select Molecule. While preparing, there shouldn't be any non-bonded atom error in the process. So this shows there is no non-bonded atoms. Now save it as 1GKC filtered.pdbqt. Next task is to make the grid box. This is to set the boundary of the docking. If you don't know the active sites of the protein and would like to search all available surface, the grid box should cover the whole macromolecule. Otherwise, you can just find the active sites of your protein of interest using this tool called cast-p. Let's see how it is done. Go to this link. It's again mentioned in the description. Click on the calculation and upload the PDB file and then submit. Now it will generate a link to which you can click and see the results of binding pockets. The active sites is in the binding pockets where the catalysis occurs. You can click on the show pockets to see many more binding pockets. Around 20 results are given for this. We'll just go with the pocket with higher area and volume. Now each of these amino acids are marked in the macromolecules in Autodock, which is highlighted in the visualization area. Once all amino acids in the binding pockets are highlighted, the next task is to make grid configuration for running Autodock. Now go to grid and click on the grid box, move and resize the grid in such a way that the binding sites are inside the grid. This X, Y, Z dimensions and coordinates will be used in the configuration file for Autodock. So now the protein is ready to go for docking. This video will be focusing on extraction of compounds from PubChem library and preparing it for the docking tutorial. PubChem is a database of chemical molecules and their activities against biological assays. It is a component of National Library of Medicine, which is a part of the United States National Institute of Health. Let's visit the PubChem website. All the links throughout the videos in the playlist will be mentioned in the description. To perform docking with the protein of interest, let's take an example of a compound, which is vitamin K. You can also search for other chemicals like curcumin, quercetin, or any phytochemicals or synthetic compounds. Here, we'll find the complete similar structures or analogs of this vitamin K to find the best compound from the list. Now we can filter the compounds based on its molecular weight and many other characteristics. Here I'm just filtering the compounds in between 344 and 444. Now go to download and mark 3D structure and click on the SDF to download the complete set of vitamin K and its analogs as a single file. Once you open it, you can see around 51 3D structures are included in the single file. Next task is to split all these SDF to individual PDBQT file for Autodock process. Open Ubuntu and go to the folder where the file exists. Once you open the Ubuntu, you will be in the root folder from where you have to come back twice by typing cd space ... and enter. So you have to do it twice. And then you need to open the mnt folder by typing cd space mnt, enter. So this will select the folder mnt. cd is nothing but the change directory short form. And then if you want to go to the next folder, accordingly you can put cd space folder name, enter. Now I'm giving the command to split the single SDF file to 51 compounds in that file. The command will be openbabel space hyphen isdf, that is input SDF, space pubchem compound name dot SDF. So whichever compound you have downloaded, that name should be given after hyphen isdf. So it will be like openbabel space hyphen isdf space pubchem compound name, or whichever name you have given in that, space hyphen osdf space hyphen capital O space star dot SDF space hyphen split. Now you can see all components are split into individual SDF files. Now remove the original file that is already split. The next task is to optimize the geometry and minimize energy for the molecules. Type ob minimize and press enter. Here we'll be selecting the force field key and the force field mmff94. Now let's type ob minimize space hyphen ff space mmff94 space hyphen n, this is number of times you want it to be minimized, a space 1000, and then the files star dot sdf. So whichever SDF files are there, all will be minimized with energy. Now press enter. It's done in 0.2187 seconds. Now we need to convert all these SDF files to Autodock format file, that is PDBQT. Type openbabel space hyphen isdf space star.sdf for considering all SDF files space hyphen opdbqt space hyphen capital O star.pdbqt and enter. Now 51 compounds in SDF formats are converted to PDBQT. Now let's sort these files based on the type and move all PDBQT files to the docking folder. Now come back to the previous folder by typing cd space ... and enter. Type ls to see the directory. Now I need the list of these ligands in a single text file for docking purpose. To make that, let's type ls space greater than symbol space ligand.txt and enter. You can see the ligand text file has been formed. This will have every file name, every compound name in the folder. Let's delete everything except the compounds in the PDBQT. You can see the receptor also inside since it was there in the folder. Delete that as well. Now save. Ligand file is also ready for the docking. In this video, we'll be discussing about the docking process and its analysis using Pip tool and visualization using Discovery Studio. Let's begin the docking using the script. Type perl space vina underscore linux.pl. All these scripts are mentioned in the description. This should be saved in the same directory of the ligands and protein receptor. So once you click enter, it will ask for the ligand file name. Now type ligand.txt and enter. Now the protein ligand docking starts. You can see the live status of docking as the percentage, and it will generate the affinity scores in both terminal as well as the individual files in the directory, along with the output file with ligand coordinates after docking. As we have 51 compounds, it may take some time to finish the docking process. Now the process done. Here you can see log files of individual docked complexes with the top 9 possible docking modes. As we have results in individual files, we need to combine all these log files for comparing the compound with higher docking affinity. Let's see how we can combine all these results. Type tail space hyphen n11 space star.log space greater symbol space results.txt and press enter. This code is nothing but copying and compiling the last 10 to 11 lines from every log files into a text file called results.txt. Now you can see the results.txt file has been generated with all the results with the header as the file name. From this, we'll be choosing only the coordinates of first result, that is with 0 RMSD. Let's see how it can be done. Open the text file in Excel, select the first column and click on the data, then text to columns. Mark delimiters and click next. Mark both tab and space for separating the results to multiple rows based on these delimiters. Click on finish. Now you can see the results split into multiple columns. Delete the first column which is not required. Turn on the filter and remove the blank which is in the end. Now move the title towards number 1. Now all top results has the heading. And now click on the filter again just above 0 and then choose 0 for filtering all results with 0 RMSD. Lower the value of RMSD you get, the higher the accuracy of docking. Now copy the complete results and paste to the next sheet. You can delete the term .pdbqt-log.log by pressing Ctrl F and then clicking on the replace all. Now you can see the compounds IDs as a list with their respective docking affinity. Let's sort the highest docking affinity now. More the negative is, higher the affinity. The drug development involves assessment of absorption, distribution, metabolism and excretion. Here we'll use a tool with free access to predict models of physiochemical properties, pharmacokinetics, drug likeness and medicinal chemistry friendliness. This SwissAdMe tool can be used by any specialist and non-experts in cheminformatics or computational chemistry who can predict rapidly all the key parameters for a collection of molecules to support their drug discovery endeavors. Now visit SwissAdMe.ch to use this tool. Here, to search the properties of compounds, we need to put smiles as a query. How to convert this PubChem compound ID to smiles? We can use PubChem ID Exchanger for this process. Go to PubChem Identifier Exchange website, and all links are mentioned in the description for easy access. I already copied all the IDs from the Excel. Paste the compound ID under the input ID list. Change the output ID to smiles. Change it to no compression and click submit job. The results are generated. Now you can click on the link to retrieve the results. Copy the smiles and paste to the Excel. Change the color to black if you are not able to see it. Now go to the data and split the text to 2. That is compound ID and smiles. Try matching with the results we got from the ID Exchanger and the compounds. You can see both are same. I'm giving the title as smiles and I'm deleting the previous IDs as it is duplicate of the compound ID in the first column. Now let's make the SwissAdMe query list. Type equal to, then click on the smiles and type and symbol quotation space quotation and symbol and then click on the compound ID, then press enter. Double click on the plus button at the corner of the cell to get the entire results in the same column. Now copy the SwissAdMe query and paste it here and run. Within a few minutes you can retrieve the results. This overall result is depicted as boiled egg here, which directly predicts the passive diffusion through the intestinal absorption to blood-brain barrier, permeation, which are the main ADME behavior impacting pharmacokinetics. The points located in the white ellipse represents compounds with high probability to be passively absorbed by the gastrointestinal tract. The points in the yellow ellipse, that is the yolk, are for the compounds with high probability to permeate through the blood-brain barrier to access the CNS. However, the white and yolk are not mutually exclusive, so all these molecules not predicted to be well absorbed nor blood-brain barrier permeate are in the gray zone. Coming to the visualization tool, I use Discovery Studio, which is freely available. Go to the main directory and open the receptor first and then define the receptor. Then drag the output which you want to explore. For example, I'm opening this output along with the receptor. Now you can see both in the same image. Now select the first result, which is the one with higher affinity score. The rest you can delete by clicking it and pressing delete button. Now click on the ligand interactions to see the interactions between protein and the compound. Now go to the interactions options and untick intramolecular interaction to see specific bond between both ligand and protein. You can also view the interaction in 2D by clicking Show 2D diagram. Now you can save this image in your directory for the publication purpose. You can choose which size you want to save it. Now the image is saved. Similarly, you can view the ligand protein in 3D following this. If needed, you can optimize graphical interface and go to the scripts, visualization and the publication quality. Then visualization of protein can be done by clicking on the receptor or selectively visualize the surface like aromatic or hydrogen bonds, etc. Now you can save this also as an image for your paperwork. Another way to see all this interaction is using an online tool called Plip. It is a web server that provides an easy to use interface which takes an input, either a PDB ID or the custom structure in PDB format. Moreover, the advanced options in the input section allows the user to modify the default settings of Plip according to their special requirements, such as adjustment to thresholds for the detection of interactions, consideration of modified residues, specification of which model to use in multimodal structures, the detection of intra and interchain interactions, and the treatment of nucleic acids. Now you need a PDB complex to be made for the analysis. So now go to the directory and open your receptor structure in PDB-QT. Then open the docked output file which you want to make complex of structure. Copy the model 1 which had the higher affinity in the docking from root to end MDL. Now paste it in the end of the receptor and save it as a separate file named as complex. Let's open it in Biomol and see how does it look. Now we need to convert this PDB-QT complex to PDB for Plip analysis. We can use a software called openbabel for this conversion. Select the input and open the PDB-QT file which you want to convert. Now we need to select the output file as PDB and then name it as complex.pdb and click on Save. Now click on Convert. Now switch back to the browser and go to the Plip website. Click on the Choose File and open the complex in PDB. Then click on Analyze. It takes a few seconds to analyze and get the results. As you can see, this is the docked image with the list of interactions. Plip also gives the detailed hydrophobic interactions and hydrogen bonds in the result section. You can download the visualization as image or Biomol format. I hope now you have studied the whole procedure of docking. Do subscribe and press bell button if you like the video and to get notified about the upcoming series of videos. Thank you.